Hello, everyone. Good morning. So today I plan to talk about the alternating series test because I look at your calendar and it looks like this week the target is to finish Power Series and Taylor Series expansion. So today we'll do AST and Absolute Convergence. And then hopefully on Friday we can start talking about Power Series and Taylor Series expansions as well. But I see that there are some questions here. Let me see. I think Morel sent some questions. Let me see what they cover. Uh-huh. So I guess these questions cover the ratio or the root test. So perhaps we can take a quick look at them before going to alternating series test. So if there are other questions regarding those two tests, then just let me know. Because I guess though the ratio and the root test are basically, I guess, the most straightforward among the tests that we use. There are a little bit of details that we need to pay attention to because it's really easy to be lost in those tiny details, especially when doing the expansions of a sub k plus 1 in the ratio test. So, okay, let me just switch worksheets here. Mhm. So if you still have questions from that, I'll be happy to walk you through them. So just send them in the chat. So let's see, worksheet 17, right? Let's call it problem 6. Okay, any particular difficulty with the first question you sent, Morel? I see that you sent the summation of 3 to the power k factorial all over 7k to the power k. I see that you got your answer, the correct answer, but any particular difficulty with this one? Or what's the particular difficulty with this?
It's just for some of these I try working out the answer and it just doesn't come out for me. So
Mm-hmm.
like it just doesn't work out.
All right, so no worries. So let's take a look at it. So for this problem, we need to determine whether this series converges or diverges. And we see that this involves exponents which can cancel each other out nicely. So I'm thinking of using either the ratio or the root test for this, even if I don't know from what quiz this is from. Because one indication that the ratio or the root test would be applicable is that if you expect some terms to cancel, some factors to cancel, and factors cancel if you have exponents and factorials, right? So my prime candidate for problems like this would be either the ratio or the root test. Now, which of those two would be applicable? Since there is a factorial involved in here, I will use the ratio test. The ratio test is suited for those with factorials. I don't think the root test would be easy when there are things involving factorials. So when there are factorials involved, chances are the ratio test would be the go-to test, right? So for the ratio test, we need to take a look at the limit of the ratio between the k plus 1 term and the k term. So we take a look at the limit of this fraction as k approaches infinity. If this is less than 1, then series converges. If this is greater than 1, series diverges. If the limit is equal to 1, no conclusions can be made. All right. So I think the main challenge here is the expansion of a sub k plus 1. So if you're expanding a sub k plus 1, that means we are simply changing all k's in the term of the series to k plus 1. So all k's you see should be replaced by k plus 1. So for instance, 3 to the power k will become 3 to the power k plus 1. And then on the second factor, k is inside the factorial. So now in the k plus 1 term, what will be inside the factorial? It would be k plus 1, right? So it's going to be the quantity k plus 1 inside the factorial. All over, I'll copy the 7, and then I have k to the power k. It will be replaced by k plus 1 to the power k plus 1. So be careful with this tiny details here. You change all k's to k plus 1. No exemptions, all right? And then for the denominator, it is simply a sub k, so I can simply duplicate this one and put it here. All right. So this is our complex fraction. We want to get its limit, but before doing so, let's try to simplify. And that's the point of using the ratio test, because we're expecting that a lot of things will cancel from the k+1 term and the k term, right? So what I'll do here is to write the quotient as a product, right? So whenever dividing complex fractions, what we do is to copy the numerator, okay, and multiply it by the reciprocal of the denominator. So it would be times 7 to the k, 7 times k to the power k, all over 3 to the power k, k to the power k. What did I do there? Not k to the k, but k factorial, right? There we go. All right, then let's try to cancel factors out. So let's see, let me use a different pen here. Okay, so I have here 3 to the power k. That will cancel with the 3 to the power k+1 on top, but that will leave us with a 3 on top, right? And then k+1 factorial, or some factors from the k+1 factorial, will cancel the things from k factorial, right? Because again, k factorial is the product from 1 until k. K+1 factorial is the product from 1 to k+1. So after that cancellation, we'll have a k+1 left on the top, right? I hope you are now familiar with canceling factorials. So expand them out, look at how they look like as products, and then you see that a lot of factors will cancel each other out. So let me know in the chat if you have some problems with that. I can give a more detailed explanation for that. But basically, we have k+1 factorial all over k factorial. That will just be k+1, right, after the cancellation. Then, oops, I have a 7 here. That will be canceled by the 7 below. So what we have so far is this. We'll have 3 times k+1 times k to the power k all over k+1 to the power k+1 times what? I think that's it. That's left in the denominator. And we take the limit as k approaches infinity. At this point,
one in the bottom separate to k+1 to the k, and then k+1 to the 1, so that way the k+1 from the top and the bottom, they cancel out?
Exactly, yeah. So there, here we see that we forgot to cancel one thing. The k+1 here will be canceled by one of the k+1s in the denominator. So essentially what we'll have after that cancellation is 3 to the power k to the k, 3 times k to the power k all over k+1 to the power k as k approaches infinity. All right. And then I can rewrite this by playing with loss of exponents. So I'll keep the 3 there. But you look at this, I have k to the power k, I have k+1 to the power k. I can write them as a single power. That is raising k over k+1 to the power k as k approaches positive infinity. All right, so loss of exponents. And then we are trying to evaluate the limit, but that won't be straightforward here because as k increases indefinitely, k over k+1 will approach 1, right? K approaches infinity, so basically this factor here will go to 1 raised to infinity, which is indeterminate because the base is not exactly 1, it's a number that goes to 1, right? So it's something close to 1 raised to the infinity. It's an indeterminate form. You can solve this limit by using L'Hopital's rule or with the additional intermediate steps of dealing with the exponent, taking the logarithms of both sides. But I guess there's a shortcut that we can use here. Something that I guess you told me about last week or last Monday about evaluating such limits. So I can do this trick. I can take the reciprocal, but at the cost of putting a negative sign in the exponent. So basically what I'll do is I'll write the base as k+1 over k, but the exponent will now be negative k as k approaches infinity, right? Because remember, the negative sign we'll just reverse the order of the numerator and the denominator, leading us back to the original expression, right? But I prefer this form because I can write this as the limit of 3 times 1 plus 1 over k raised to the power negative k as k approaches infinity, right? Simple fraction, simple division there. Exactly, Nathan. Yeah, because this limit, remember, maybe I'll put that here. So recall, if you're taking the limit of 1 plus a over k to the b power k as k approaches infinity, this will just be e to the ab, right? So if you have this particular form, and luckily we have that, and that's the reason why I wanted to take the reciprocal and do the division thing, right? So here we only need to take a look at what's the value of a and what's the value of b. In this case, value of a is 1, value of b is -1. So definitely, so the limit will become 3 to the power e times 1 times -1. So it's going to be -1, all right? So essentially, this is 3 over e.
So if you're able to get like an answer out of it, that means it converges?
Not exactly, because the thing is that you need to compare it with 1.
Okay, it's just because it's asking for if it converges or diverges.
Remember the ratio and the root test. You take the limit of either the ratio or the root. If the limit is less than 1, it's convergent. If the limit is greater than 1, it's divergent. If the limit is 1, no conclusions can be made. So at this particular point, we found the limit. It's 3 over e for the ratio. And remember that e is 2.71 something. So the denominator is smaller than the numerator. So that means this guy is greater than 1, right? So by the ratio test, the given series diverges. All right. Now this is different from the basic test for divergence, because the basic test for divergence tells us that if the limit is not equal to 0, then it is automatically divergent. But the ratio in the root test requires you to compare the limit of either the ratio or the root to the number 1, and you can get appropriate conclusions. So this one's divergent. Okay, is that fine? Okay, no questions, no follow-up questions here. I see there's another question here, which I find to be interesting. So maybe we can still take a look at it. And then I guess after this, we can go to alternating series test, and Herson has a few questions about AST. He has a nice point here. What if the limit equals 1 when you do the ratio test? It's inconclusive. Morel is right. So you need to try another test. So yeah, John is correct. Yeah, you need to do something else when the limit is equal to 1. That's the limitation of the ratio in the root test. Okay, so let's see. The other question is this, which is quite interesting. We need to find the sum to check if the series 6 times k factorial squared all over 2k factorial converges or diverges. Now, here's where you will see the utility of the grouping symbols. Grouping symbols are very important because they will remove the ambiguity in the given problem. And this will tell us exactly what is inside a factorial, what is inside a square, and so on. And this will remove, as I've said, all the ambiguities in the problem, so you will not have those memes that ask people what would be the sum or what would be the final answer, and people in the internet are having a big debate or fuss over it. But essentially, it's just about interpreting the grouping symbols. Okay, so let's see with this one. So there are factorials involved. So what I'll try to do is to use the ratio test here.
When do you suggest to use the ratio or root test?
Okay, I use the ratio test if there are factorials involved. Why? Because when you when you take the ratio of a sub k plus 1 and a sub k, and there are factorials involved, most of the factors will cancel out nicely. Now, you will use the root test if you have exponents, if you have k's in the exponent. So if you have terms like k to the k or 3 to the power k plus 2, I suggest you use the root test. Because essentially what the root test does is you take the the kth root of this and take the limit as k approaches infinity, right? So the kth root will essentially cancel the exponent k, which will give you an easier expression to take the limit of. So ratio test, if you see that things will cancel out, especially if you have factorials involved. Root test if k lives in the exponent. Okay, so here I'll use the root test, the ratio test. I won't use the root test here because there are factorials involved. So I need to take the ratio of a sub k plus 1 and ak as k approaches infinity, right? This would be a big fraction. A sub k plus 1, I'll replace all k's by k plus 1. So we need to pay attention to the grouping symbols. So 6 is outside the factorial and outside the square, so 6 will just be copied over. And then inside the square is your factorial, so still something squared. But this time, instead of a k that is inside the factorial, I will have a k plus 1 inside the factorial. But the k plus 1 factorial remains inside the square. All over, okay? So here, inside the factorial was 2k. So in the next term, I will have 2 times k plus 1 that will be inside the factorial. All right. So I'll replace k by k plus 1. Note here that k is multiplied by 2. And then I take the factorial of the product. So in the k plus 1 term, I'll multiply 2 by k plus 1. Whatever the product is, that is what I will factorial, right? Or what I'll put inside the factorial. And then the k term is just this guy copied over. So let me duplicate that. And that's what we have here. And we take the limit as k approaches infinity. Now I'll turn it into a product so that we see which cancels out. So here, duplicate this guy times the reciprocal of the divisor to k factorial all over 6 times k factorial squared. All right. Now I will rearrange some of the terms here of but before that, maybe I can cancel the 6 already here just to get rid of that constant there. And then I'll play with this guy and this guy. They are both inside squares, right? They both have the exponent 2. So I can write them inside a big square. So I'll have k plus 1 factorial on top and a k factorial at the bottom, right? So that takes care of this and this guy. And then I'll have a 2k factorial. What does 2k factorial mean? So it means that I will multiply all numbers from 1 through 2k. So it's going to be 2k times 2k minus 1 times 2k minus 2 all the way down to 3 times 2 times 1, right? That's what 2k factorial means. We take the product from 1 all the way up to 2k. Right? Just expand it out so that you see exactly what happens. Now this guy is what? This is upon expansion. This is 2k plus 2 factorial, right? Because we need to multiply these two guys first before putting them in, before taking the factorial. So it's going to be 2k plus 2 factorial. But what does this expression mean? It means we take the product from 1 all the way up to 2k plus 2, right? So upon expansion, it would be 2k plus 2, 2k plus 1, 2k, 2k minus 1, 2k minus 2, all the way down to 3 times 2 times 1. And we take the limit as k approaches infinity. And let's see what cancels out. So here, oh, I have 2k all the way to 3, 2, 1 can be canceled by this guy, 2k all the way down to 3, 2, 1. All right. And then k plus 1 factorial versus k, there would be what? There would be a k plus 1 that remains on top, right? Because this guy is product from 1 until k plus 1 factorial. The denominator is just a product from 1 till k. So after cancellation, there would be a k plus 1 left on top. So essentially, let's collect what remained. So we'll have a k plus 1 quantity squared all over. In the denominator, we'll have 2k plus 2 times 2k plus 1 as k approaches infinity. All right, all good?
Can you explain the 2k plus part where you canceled it on the right?
This guy, all right. So what I did there is to expand everything, right? So the top has a 2k inside the factorial. So remember what factorial does, or what the factorial does. So all we need to do is to just multiply all numbers from 1 until 2k. So this is the product from 1 until 2k. So if I expand it out, I'll have 1 times 2 times 3 all the way until 2k, right? That's what 2k factorial means. And then the other guy, this is 2k plus 2 factorial. So it's the product from 1, 2, all the way up to 2k plus 2. And that's what I have here in the denominator. 1 times 2 times 3, all the way up to 2k plus 2. And then I compare what are the things that I can cancel that that are both in the numerator and then the denominator. You see that here I have starting from 2k all the way to 1. And that's essentially this until this. So they will cancel each other out, leaving us only with this guy. All right, is that good? All right, and then Maria has a question. After cancellation, would it be just k plus 1 factorial or just k plus 1? It will just be k plus 1. I'm guessing you mean here, right? Because if you expand the top, it would be the product from 1 to k plus 1, right? K minus 1 until 3 times 2 times 1. All over, k factorial is the product from 1 till k. Right? So the expanded products, the expanded factorials look like this. And what you can notice here is that, oh, they both have k until 3 to 1, from k to 3 to 1. So all that remained was a k plus 1 here. Sure, Herson. Just send your question there. All right, are we clear here? So it's just playing around with the factorials. If you cannot see exactly what happens, you can expand the factorials, right? And do the cancellation manually. Just take a look at the pattern, right? And then what do we have now? We have the limit of a polynomial over a polynomial. Here, the highest power is k squared, right? In particular, you will have a k squared. In the denominator, what would be the highest power? We'll also have a k squared, but what's the coefficient of k squared? When you expand it,
1/4.
Exactly, because the denominator will have a leading coefficient for k squared, right? It doesn't matter what the last two terms would be when you FOIL the denominator, right? But both of them has power 2, so that means the limit as k approaches infinity is just 1/4, which is less than 1. So by the ratio test, the series converges. Okay.
Thank you so much.
All right, you're welcome. Let me see. Okay, so I think Herson has a question. Where's my pen? There we go. let's see. You said you got limit equal to 1, thereby requiring you to to use a different test. I guess you're right. The ratio test here would be inconclusive. Let's see why. Sum of 3k factorial all over k plus 6 factorial. And we take the limit, sorry. Okay, there we go. And maybe now we got used to using the ratio test whenever we see factorials. That's not a bad instinct to have, right? So let's try ratio test. So you take the limit of a sub k plus 1 all over ak as k approaches infinity. This would be the limit of, be mindful here, 3 is outside of factorial because there is no grouping symbol putting 3 inside a factorial. So you just copy 3, then k plus 1 factorial all over. We replace k by k plus 1. So that would be, the denominator would be k plus 7 factorial all over 3k factorial all over k plus 6 factorial. Yeah, sure, John. I'll just finish this ratio testing and then go to alternating series test, right? And I guess Herson has some questions that we can work on for that. Okay, so, right, so I have set up the ratio here. I'll turn it into a multiplication problem to see what can cancel. Okay, as k approaches infinity. Now what you see here, the 3's will cancel each other out. K plus 6 factorial will be canceled by k plus 7 factorial with a remaining k plus 7 in the denominator. And I hope you can now see the pattern there. This is the product starting from 1 until k plus 6. This is the product from 1 until k plus 7. So if you cancel those common factors, there would be a k plus 7 left in the denominator. In the same manner, k plus 1 factorial is the product from 1 till k plus 1. K factorial is the product from 1 till k, so there would be a k plus 1 left on the numerator. So what you have after all those cancellations is we'll have a k plus 1 left on top and a k plus 7 left on the denominator. And unfortunately, the limit is equal to 1. So ratio test is inconclusive. We'll need to try another one, right? But for this guy, I can actually simplify this a bit. All right. So I can use the basic test for divergence here. Right? Because you see that I can simplify. We forgot to simplify this because the top is the product from 1 till k. The denominator is the product from 1 to k plus 6. So you can simplify it as 3 over k plus 6, k plus 5 times k plus 4, all the way down to what? All the way down to k plus 1, right? That's how the denominator will look like. Or actually, the basic test for divergence will not work here. Because, because the limit will be equal to 0. So instead, I'll use the basic, I'll use limit comparison or the comparison test here. Not BDT, because you see here that this limit will go to 0, right? So yeah, I'll use direct comparison test here. I'll compare it with this series. I'll copy the 3, and I'll have k to the power 6. Oh, it would be larger. I'll be making the denominator smaller. Okay, that's fine. This would be k to the power 6. And I guess this fraction is larger, or this series would be larger. Okay, why will it be larger? Because all I did there is to replace k plus 6 by k. replace k plus 5 by k, replace k plus 4 by k, all the way to k plus 1, which will be replaced by k. So in all, the new denominator will be smaller than the previous denominator. So this guy is smaller than the previous denominator. And if you have a smaller denominator, the fraction is much larger. So that means this series here will be smaller than this series. The trick, Maria, is I would like to answer it's just instincts. But the thing is, I want to compare it with k to the 6 because I know that k to the 6 will converge, right? Because 1 over k to the 6 is a p series with p equals 6, which is greater than 1, so it converges. Now, it is convenient actually because I see here that all the products are larger than k, right? So I have a k plus 6 here, I have a k plus 5 here, I have a k plus 4 here, until I get k plus 1. So what I'll do is I'll replace all of those factors in the denominator by k. So k plus 6 will be replaced by k in the new series. K plus 5 will be replaced by k in the new series. K plus 4 will be replaced by k in the new series. And there would be 6 of these, right? Until I reach k plus 1. So essentially, all of the new denominators are smaller than the original ones. So this guy is smaller. So that means the entire fraction is larger. And hence, I use this inequality, right? And the good thing about this is convergent. So which is a convergent p series with p equals 6 greater than 1. Remember, p series converge when their p-value is greater than 1, right? So that means the given series is smaller than a convergent series. So this guy is finite, so this must also be finite. So the given series is convergent. All right. So a little bit of tricks there, but hopefully you'll get used to them. So try answering this test. Make sure you get familiar with this, and you will pick up some bits and pieces or some tricks along the way. Yes, Ferguson. I think that's the way to go with it. So the first thing you do is look at the series. If it's see if it's a special series. I mean, is it a p series? Is it a geometric series? Is it a telescoping series? Because those are easy to spot, right? Now, if they will not fall under the special series that we have encountered, then try basic divergence test because that is easy. You can actually run the test in your head. So if the limit is equal to 0, then you need to go and move on to another test. If the limit is not equal to 0, then BDT applies, then you can write your formal solution. So that's your second go-to thing. Try the BDT. If BDT doesn't apply, then you try the ratio or the root test, right? And they are specially designed for powers and factorials. Now, if the ratio or the root test doesn't apply, then try comparison tests. And then the integral test will come last, right? The basic comparison test and limit comparison test is a little bit tricky, but I suggest try limit comparison test rather than the basic comparison test because BCT is quite limited in scope. So yeah. So yeah, get familiar with those things. Try to answer problems from the exercises on the BCT and the LCT, because there's no hard and fast rule for them. I mean, what would be the testing series? I think they will just come in as as an instinct to you, and you will know exactly what to compare it with. But I'll say a couple of words on that perhaps later when we have time. Just remind me to give you some more examples about the basic comparison and the limit comparison test when we do the review for the final exam. All right. Or for test 4, I guess test 4 is still coming up. All right. So Okay, so I guess this is a good time to transition to the alternating series test and compare and the absolute convergence. So let me see worksheet 18. Now, for the alternating series test, just a quick recap. So you will be given a series that looks like -1 to some power, say n or n plus 1. The thing here is that this guy should take care of the sign change between two consecutive terms. And then you have a sub n, which is a positive or a purely negative term, but we'll assume that an is positive. And then the test says that we need to check for two things. So if the following holds, test one would be a sub n plus 1 is smaller or equal to a sub n. This means we have decreasing series. I don't know what the exact version of the ACT that was given in the lecture. We say that this should be true. The most basic AST or alternating series test requires this to be true for all n's. But actually, you can easily deduce that if this will hold for starting from a large n, then AST will still apply. But I guess you just deal with the most basic one and check if it's decreasing. And then, okay, I don't think an S should be there. So, and then the next thing is you take the limit of a sub n as n approaches infinity, and this is equal to 0, then the alternating series is convergent. Right. Now, this is important. You need to show that these two things are satisfied to conclude that the given series is convergent. I guess most of the times this one is easier to see. So I suggest you try to take the limit first and then go on with the test for a decreasing if the terms are decreasing, because for complicated series, condition 1 is harder to check, right? But what happens if the limit is not equal to 0? So just a quick note, but if the limit of an as n approaches infinity is not equal to 0, then you can conclude that the series is divergent, not by the AST, but by the basic test for divergence. So if the limit of an as n approaches infinity is not equal to 0, then the limit of -1 to the power n, a sub n as n approaches infinity, right? So if this guy doesn't go to 0, so if you throw in the alternating sign there, so that means this limit won't exist, right? So then this limit won't exist. So the given series, so the alternating series will diverge by AST. Oh, sorry, will diverge by BDT. Well, Dimin Jan, this note or caveat I put in here, you can just say that, okay, you'll solve for the limit. It's not equal to 0, right? And then you will say that the limit of this guy, if you throw in the negative sign in there, will not exist, then this would be divergent by BDT. I guess the keywords that we'll be looking for would be this phrase here. Make sure to put this into your exam or in the free response part.
For the part above it, the 1 and 2, do we have to prove those, or do we just write those down?
Okay, 1 and 2. Mm-hmm. Well, you need to do some calculations here. I'll try to go through some problems, and then hopefully you'll see what will I expect out of the AST from you guys when you're doing the homeworks or the FRQ in the exam. Some of them will require little work. It's just like it is just formalizing your thought process, because that's one main difficulty with this setup that we have. You're taking the test at the comfort of your homes. So graders had been a little bit more strict because we don't know if you just copied it from somewhere or if you got it from one of your classmates. So you need to put as much details as you can. But if the solution or the step is very obvious, then we won't ask you for anything, right? So let's take a look at some problems. So perhaps, okay, let's start off with this one. So in worksheet 18, I copy pasted the exercises from section 9.6, so you can try them out. So and then I also lifted some examples from the Lamar tutorial that I shared with you guys last time or in the previous worksheet. So I won't eat up some of the exercises that you can play with. So let's try the following. So first, I'll have the series -1 to the power n of n squared over n squared plus 5. So I'm jumping here from the index from the dummy variable k to n, so we'll use them interchangeably. But here I'll use n. Okay, so let's see. As I mentioned, condition 2 is much easier to evaluate, right? So we simply need to take the limit of the positive term. So because AST, if you remember, requires us to get the limit of an, where an is the non-alternating factor. So essentially, we'll just ignore the alternating sign. So in this case, the alternating sign is due to -1 to the power n. So I'll just look at n squared over n squared plus 5 and take the limit as n approaches infinity. So here, what I'm trying to do is to check if AST applies. And again, the AST will only apply if the two previous conditions that we have stipulated are met, right? If one of them fails to hold, then AST will not apply. So I'll go first with the limit before taking a look at is it increasing or decreasing, right? So here I have the numerator is power 2, denominator is power 2. So the limit is equal to 1, which is not equal to 0. This means that AST doesn't apply or is inconclusive, right? But the fact that the limit of the positive factor is equal to 1, not 0, then the limit of -1 to the power n times n squared over n squared plus 5 as n approaches infinity will not exist. I hope it's clear to you why it will not exist, because without the alternating series, this will approach 1. So in the list, in this sequence, right, the terms will just oscillate between plus and -1, right? Because this factor will go to 1 in the long run. But if you throw in the alternating series, so that means the terms in the series will essentially become -1, +1, -1, +1, and so on. And so in the long run, this limit will not exist. So the series is divergent. By the BDT, the basic divergence test. All right. So I just want to be clear here. The conclusion was given to us by the basic divergence test and not the AST, because AST is inconclusive because it will require the two conditions to be met. ANs must be decreasing and it must go to 0. But here the limit doesn't exist because the limit without the alternating sign is not equal to 0. Okay, so I guess this will suffice as a full solution. So if you write something like this, then you should be good. You should get full credit for a particular problem. All right, is that good? Let's try another example. Let's try summation from 2, let me use k here, to positive infinity of cosine k pi all over root k. Now it's not obvious that this is an alternating series, right? But it is an alternating series because cosine of k pi is what? When k is equal to one, the starting value is 2. Oops, the starting value is 2. So if k is equal to 2, what is cosine 2 pi? Cosine 2 pi would be 1, right? When k is equal to 3, you'll have cosine of 3 pi, but cosine of 3 pi is -1. Then when k is 4, you have cosine 4 pi, which is 1. Cosine of 5 pi is -1, and so on. So essentially, cosine of k pi is equal to 1 if k is even, right? Because in the unit circle, even multiples of pi will be here. So 0, 2 pi, 4 pi, 6 pi, and so on. They will be here, and the cosine here is +1. And when k is odd, you will be here, right? So because you have pi, 3 pi, 5 pi, 7 pi, and so on, they all are here, and the cosine at this point is equal to -1. All right, so we can rewrite this series as this: summation from 2 to positive infinity of -1 to the power k all over root k. Is that good? Do you guys follow? We can check. When k is equal to 2, we'll have -1 squared. That's +1, which fits this, right? When k is 3, we have -1 to the power 3, and that would be -1, which is true because k is odd. All right. So that means this given series is -1 to the power k all over root k. So the positive factor here is 1 over root k. So we'll take the limit of 1 over root k as k approaches infinity. And this is equal to 0, obviously, right? We'll ask no questions about it as long as you write it this way, because it's obvious. When k becomes large, 1 over k will go to 0. That will give you perfect credit, or that should give you perfect credit. Let me know if you got deducted, if you got points off by simply writing this. I guess that's obvious. And then let's check if it's decreasing, right? So note that 1 over root k is decreasing. And I guess no questions asked about that because it's obvious, because the denominator increases, right? So as k increases, the numerator remains the same, the denominator increases, so you get smaller and smaller values. So I don't think there would be questions asked if you just mentioned that a sub k, which is basically 1 over root k, is decreasing, because it's obvious from how it looks like, or by definition. So no much work will be expected from you on that. So since the two conditions of the AST are met, then we say that, okay, so by the AST, or the alternating series test, the series cosine of k pi over root k, k going from 2 to positive infinity, converges. And I guess that's a full solution. That should merit you full points for this problem. Okay. Now let's try another one. Perhaps now something that will require more work. Just to let you know what's my mindset when I'm grading your grading papers, and what I'm exactly looking for in your solutions. So for instance, we'll have this. It's almost time, so I'll understand if some of you need to leave, but maybe I'll have 2 more minutes or 3 more minutes to finish this problem up. Okay. Now I'll start with the limit test and see what the limit would be, right? So I'll try to use AST. First check is to take the limit of the positive part. The positive part is negative, is the root n over n plus 4 as n approaches infinity. And obviously this is equal to 0. Again, no questions asked because what I'll expect you, or I trust that you know the shortcut. The numerator is degree 1/2 or has largest exponent 1/2. The denominator has largest power 1, so that means denominator wins. The denominator grows a lot faster than the numerator, so the limit is equal to 0. I want to require a lot of work here. If you want to be sure, you can use L'Hopital's, but I guess we have the Bobo trick here. Bigger on the bottom, so the limit would be 0. That's good, that's cool. You can leave your solution like this. The next thing is it decreasing? Now, if you look at the n term here is root n over n plus 4. To me, it's not clear if it is really decreasing, because when n increases, the numerator increase, but the denominator also increase. So both numerator and denominator increase. So I don't know what wins. Do I get a larger fraction or do I get a smaller fraction? Because remember, when the numerator increases, then the entire fraction will increase, assuming that the denominator doesn't change. If the numerator is fixed and the denominator is increasing, that means the fraction will decrease. But if they will both increase, I don't know what will happen. It's not clear to me if the new fraction will be larger or will it be smaller. And for those instances, I want to show I want to see some work to prove that the root n over n plus 4 is decreasing. Now, there are several ways on how you can do it. So one approach which I like is to consider the function root x, over x plus 4. I'll take a look at the derivative. Remember, when the derivative is positive, then when the function is increasing. When the derivative is negative, then the function is decreasing, right? So I don't know if this is the best way to show being decreasing, but this is usually my go-to test. You can try other tests for being decreasing or increasing. Do the method you're more comfortable with. So if I look at f prime, I hope this is easy. So I square the denominator, low derivative of the high, but the derivative of the high would be 1/2 x to the negative 1/2 minus high derivative of the low function, which is 1. Is it clear that this is negative? Because this would be x plus 4 over 2 root x minus root x all over x plus 4 quantity squared. Did I take the derivative properly? Low squared, low derivative of the high minus high derivative of the low. Okay, maybe a little bit more work will give us this. Simplify the numerator. I'll have 2x all over 2 root x over x plus 4 quantity squared. Right? So I just added these two fractions to a single one, right? The least common denominator is 2 root x. Now I think it's clearer because the numerator now would be 4 minus x all over 2 root x, x plus 4 quantity squared. And this would be negative if x is what? If x is greater than 4. So I guess I need to cheat a little bit here. Start the sum from 4 until infinity. so that I know that this will be decreasing all throughout my series. But that's the thing, because the more general statement of the alternating series test is that the condition is that the terms in the series will eventually decrease. So starting from a number until you reach infinity or until you go to larger indices, you should see a decreasing behavior. So instead of condition 1, which tells us that the positive factors are decreasing, you can just say that they will decrease eventually. And that's what happened here. But just to cover my bases, I would just like to start the summation at 4. So I will comply with the requirements of the AST that I gave in the at the start of this notes, right? So the derivative is negative, so A sub n is decreasing, and we have shown that it is decreasing to 0. So by AST, the given series converges. Okay. So whenever it's not obvious, you need to give a solution or ample justification for your answer. All right. Now I plan to give some more examples about AST, but we did a lot of items for the ratio and the root test, which is fine. So maybe let me know on Friday if you still have some questions or do you want some clarifications about the AST next time. But one thing we didn't cover today is checking for absolute convergence. So we can go over that and the remainder theorem or the error estimate for alternating series before going into power series and Taylor series expansion. I guess it was fine that we went over the ratio test one more time again today, because I guess you already seen that to get the radius of convergence of power series, we need to apply the ratio test. So it's a good thing you brought up the ratio test again, because we will meet them again when we go to power series. All right. So I need to run, guys, but I hope I answered most of your questions today. Let's do this again on Friday. All right. Bye, everyone.